All right, welcome back. Let's continue with section 3.5. We've already talked about vertical and horizontal translations and reflections. Now we're going to talk about vertical stretches and compressions. All right, so we're just going to jump right in with the definition first. So if we have a real positive number, so a is greater than 0, then if it is between 0 and 1, so if it's a fraction, it's going to represent a vertical compression when you multiply by it on the outside. And if it's bigger than 1, it's going to be a stretch by a factor of a on the outside. So let's look at a function for an example of this. In the middle is my original function f of x in sort of the navy blue here. That's my original function. If I multiply by that function by 2 on the outside of the function, that means for each input value, I'm going to double. So you can see it goes from here up to twice as high as it was. So if this was initial value, this is twice the value. And that's going to be true for every value of x. If I come over here, and there's my initial output value, then I double that output value for my stretch. All right, likewise for compression. If I have by a fraction, like 1/2, then, sorry, I can't think and erase at the same time. If I multiply on the outside by a fraction, like 1/2, then it's going to take every input value, compute the output value, and then divide that output value in half. So if this was my initial input value here, half that value is down here. So this is my initial value, this is my half. Same down here, and you can see that half of a smaller number is less of a difference, right? So here's my output value, here's half. So whatever output value I get, I take it and divide it in half. Let's do an example and see if we can work this out for ourselves. All right, here is a nice graph of a function. We're going to first try to stretch the following graph by a factor of 2, and then we will compress by a factor of 1/2. All right, so let's start on the left at 0, where the function's domain begins. And if we're going to do stretching first, and I'll do that in green, stretch in green, our output value is 1, so our new output value is twice that, which is 2. And let's pick another one. Let's go to x equal to 3. My output value at 3 is also 3. So my new output value, so this one went from 1 to 2, my new output value is going to be twice 3, which is 6. So this guy went from 3 to 6. And I have a curve up here. I can even do one in between if I want to. If I go to like 1, it looks like about 1 1/4. Double 1 1/4, and you get about 2 1/2. So this one would go about here. And then I can connect the dots to make a nice curve. So, and let's see, that's really close to 4 here. So if I want to do the first piece of my stretch, it would look like that. Since the next piece of my graph is a nice straight line, I'm just going to jump to the end. At input 6, output is 2. Double that, output would be 4. So I draw that piece in. And finally, if input is 7, output is 0. Double of 0 is still 0. So that actually just stays the same. So there's my vertical stretch by a factor of 2. Let's try and do a compression. I'm going to switch colors. All right, so we go back to the beginning. At x equal to 0, the output was 1. Half of that would be a half. At x equal to 1, the output we decided was about 1 1/4. Half of that is about, I don't know, what is half of 5/4? 5/8, just over here. This one is really close to 2, so it's going to be close to 1. And finally, half of 3 is 1 1/2. So there's my first piece. All right. My input at 6, for input value of 6, my output was 2. Half of 2 would take me down to 1. Connect that with a straight line. And again, half of 0, input is 7, output is 0, half of 0 is still 0, so that guy stays the same. So this is my compress, the blue. So we just took each of our output values, either doubled them for stretching or compressed for or divided by a half, or not divided by a half, multiplied by a half for a compression. All right, let's talk about horizontal stretching and compression. And just like shifting and translating, if it happens on the outside of the function, it's vertical, and if it happens on the inside of the function, it's horizontal. If you multiply by a, and a is a fraction, we're going to stretch by a factor of 1 over a if it's a fraction, and we're going to compress if it's a number larger than 1. So let's go ahead and see what that looks like. So here's my original function, y equals x squared in blue. Let's go to input of 1, output of 1 on my original function. 1 squared is 1. If I take my input of 1 and multiply it by 2 first, that gets me to 2. And my output of 2 was 4. So now what happened at 2 is now happening at 1. Right? So that's my vertical stretch, my horizontal compression. It's making things happen faster. So what happened at 2 before, which was 4, is now happening at x equal to 1. Right? So that's where I get that point. And then of course 0, 0 is the same, that if you multiply a 0 by half or double it, it's still 0. Let's do another one on this horizontal compression point. Let's look at x equal to -1. On my original function, an input of -1 gave me an output of 1. If I multiply that -1 by 2 first, that gives me -2. What happened originally at -2 is now happening at 1 on my compressed function. All right, so let's talk about horizontal stretching by a factor of 2. Let's go back to the same points, and I'm going to switch to the other color. Thinking about 1, 1 again, if I multiply that by a half, then my input is now 1/2 instead of 1. Half was way down here, so what happened at a half is now happening at 1. Let's look at another point. Let's look at the point 2, 4 on my original function. If I multiply that 2 by 1/2, it's 1. So what happened at 1 before is now happening at 2. And that's why it's being stretched out. Things are happening slower. What happened at 1 before now happens at 2. What happened at 4 before, what happened at 2 before now happens, I'm saying that backwards. Stop. What happened at 1 before now doesn't happen until 2. What happened at 2 doesn't happen until 4. Things are happening more slowly when you do a horizontal compression. Let's look at an example, see if we can get this to work out. Let's look at this graph and let's stretch it by a factor of 1/2 and compress it by a factor of 2. So a horizontal stretch of the following graph by a factor of 1/2 would be f of 1/2 x. Okay, so let's do the horizontal stretch of the following graph by a factor of 1/2. So that's f of 1/2 x. The horizontal stretch of the following graph by a factor of 1/2. So we're going to stretch it horizontally by a factor of 1/2. Let's start at x equal to 0. If we plug in and try and graph f of 1/2 x, if we plug in x equal to 0 into this function, we get 1/2 of 0. That's still 0. And we take f of 0, we can see at 0, f of 0 is 2. So that's still a point on our new graph. Let's try another point. Let's try x equal to 1. At x equal to 1, let's actually try x equal to 2. Let's try x equal to 2. If x is 2, 1/2 of 2 is 1. The original function at 1 is about 1 3/4 right here. So f at 1 is 1 3/4. About. So I'm going to come over here now. At x equal to 2, my output is 1 3/4. So what happened here is now happening here. Let's try one more value. Let's try 4. Half of 4 is 2. The original function value at 2 was equal to 0. So now f at 4 is equal to 0. So what happened at 2 is now happening at 4. So you can see we're stretching horizontally. And so if I connect these dots, I get a nice stretched ellipse out there. Well, that's not the best drawing ever, but you get the idea. And if I'm going to do the same thing on the other side by symmetry here, so that's going to look like that. So that's my stretching of the graph by a factor of 1/2. Let's try horizontally compressing by a factor of 2. So let's get a different color and let's do f of 2x. Let's make the same little chart. X twice x, and let's figure out what f of 2x would be equal to. So at x equal to 0, twice 0 is still 0, so it stays the same at 2. So we still have this same point here. At x equal to 1, twice 1 is 2. The original function at 2 was 0, so now this is going to be 0 at 1. And I think we can see that what happened at 2 is now going back to 1. So we're going to look like this and like that for our horizontal compression. These are a little tricky and take a little bit of practice. All right, so let's